Thank you. Okay, so today's topic is using Kafka with microservices. First of all, we will discuss what is the microservices concept or what is microservices architecture. Then we will discuss what is Kafka, what are some of the core concepts involved in Kafka. And then in the end, I'll discuss how we can utilize Kafka in a microservices architecture-based application. Okay, so the slides will be made on the same website that you guys used for registering to this webinar. So you'll be able to see the slides as well as the recorded session as well. Okay, so first of all, let's discuss what is so microservices is not a very new concept anymore. It has been in place for quite a while now. It became very popular because of methodologies like Scrum, etc., and also because of DevOps. So DevOps is also a very popular concept these days, continuous integration, continuous delivery, etc., and so on. Heavily benefits from methodologies and from DevOps, or in fact, all these three things, they help out each other. We get to get the best of all these technologies if we utilize all of them in a single project. So first of all, let's discuss what is microservices concept. So as the name suggests, microservices, they are small autonomous services which work well together. Think of small autonomous services. For that, we have to basically think of our traditional architecture, first of all. I'll show you some examples in just a bit, but traditionally we used to have monolithic sort of architecture. We used to have very fat server sort of concept where we had lots and lots of services hosted on pretty much the same server. The database, the services, etc., they all used to be on the same server basically. And microservices, it's not just about sort of your services across multiple machines. We'll discuss this concept in more detail in just a bit. But generally speaking, microservices, they're overall independent of each other, basically. And definitely, you'll want to have some taking place in between as well. So if you have lots of this, then you'll not want to just leave them running in an independent manner. You'll still want to have mechanism in place. And that is where Kafka comes. So overall, microservices, they are processes or independent services, basically. They communicate over APIs, REST APIs. Although you can use SOAP-based services as well, but microservices heavily benefits from the REST services concept. And rather than letting the application connect to some database, you basically restrict access to the databases by creating services in between. The requests, they will get sent to some service, basically. And the service will be responsible for opening a connection to the database and then fulfill the request and so on. And one of the benefits of not letting the application directly connect to the database, you'll make the application sort of more cross-platform. You'll make it technology independent. So we do not have to rely on a specific technology like .NET or Java or Node.js, etc. So it's totally independent of the technology. And microservices, it is a form of SOA, service-oriented architecture, but it's much more than that. Architecture, it has been existing for a very long while. And traditionally, we used to rely on it. Let me actually give you a quick overview of some between microservices and the classic SOA approach. So traditionally, we used to rely on SOAP-based services. We used to have XML as the data interchange format. Whereas in case of microservices, we mostly prefer using JSON or JSON, depends on how you Well, it's totally up to you how you pronounce it because it's not really a proper noun. So it's basically the JavaScript object notation. It's just the data interchange format. And in case of SOA, they used to be complex to integrate because it used to heavily rely on XML, etc., and so on. And it used to be a very monolith sort of system. It used to be a huge system. Services, they are smaller in size. So usually it's easier to integrate. They are almost like plug and play sort of services, basically. So you get to design such a way that they should be able to integrate with each other. They should be able to communicate with each other, and so on. And traditionally, SOA-based services, they used to rely on HTTP and SOAP, whereas microservices, it still uses HTTP or HTTPS, and it mostly utilizes REST-based services because REST services, they are very lightweight services compared to the SOAP-based services. Let's look at an example of the traditional enterprise application architecture. So traditionally, we used to have multiple layers. Like if you have a three-layer architecture, we would have a client side or the user interface, where you will have HTML and JavaScript. You will have, and JavaScript-wise, you can use jQuery, you can use AngularJS, Backbone, doesn't matter framework you're using on the client. And you will want to have some database as well, like is Oracle, SQL Server, MySQL, DB2, etc. Or you can also choose no SQL-based database as well. For example, MongoDB, Cosmos DB, CouchDB, and so on. And the reason for using NoSQL-based databases would be you want to have faster performance because the relational databases, they are usually slower to write to and to read from and so on. Whereas when you use the NoSQL-based databases like MongoDB, Cosmos DB, CouchDB, etc., they are very, very fast. And another benefit is that they do not have any schema at all. You get to store the data usually in object format or in JSON format, usually. Otherwise, it can be just a bunch of numbers or something like that as well. But obviously, in a real world scenario, you usually rely on some proper format like JSON, etc., and so on. So you store the data in a NoSQL database, and then later on, when you want to consume the database or the data from the database, that is when you define the schema. So you sort of define the schema at runtime rather than defining it upfront and slowing down things a lot and so on. And usually it also helps out a lot when we utilize big data sort of concept as well and so on. So it's still up to you whether you want to use NoSQL sort of databases like MongoDB, etc., or not. Otherwise, you can still definitely choose to use Oracle, SQL Server, etc., and so on. Then on the server side, you would have some technology like Java, .NET, PHP, Node.js, which runs on the server side and so on. So this is usually architecture where we have these three layers basically. Let's look at the simple diagram. I already have it here. Okay, so traditionally we would have a web browser where the end user will be able to perform some operations like enter the values in the fields, click on some button, etc. And then a request would get sent to the server. And on the server side, you could definitely have multiple servers that are load balanced. Like you could have Tomcat, Apache web server, or whatever server you're using. You can load balance the server. So here, let's assume that we have load balancer involved as well. And we have, let's say, multiple Tomcat instances and so on. So one of this Tomcat server in this particular case, give the request. And here we have the whole application deployed. So here we are assuming that we have a Java-based application since we are taking this Tomcat as an example for now. So here we have some WAR file, web application archive file, and it contains everything. It contains the JSP files, the HTML, etc., and so on. So the storefront UI is stored here, and all the services, they are also the same application on this same server, on the same Tomcat server running on a given machine. So let's say we have various services. These can be SOAP-based services or REST-based services. So let's say we have a catalog service, we have order service, customer service, etc., and so on. And then all these services can connect to some database as well. So database-wise, let's say we have Oracle or SQL Server or something like that. So here you can see that this is a monolith. It's a monolithic design. We have designed or stored centrally, basically. The whole application is sort of a centralized application. So this is the traditional architecture. Whereas if you use microservices concept, it would be something like this. So here, I'm taking a slightly different example, but overall it's the same concept. So here, rather than having a monolith system, now we have multiple smaller services. First of all, we have any client browser on the end user machine, and then end user will interact with the application, send a request to the server. And on the server side, we have multiple smaller services. This is a microservice architecture, basically. So here, let's say we have account service, we have product catalog, card server, etc., and so on. These are services, basically. Let's assume these are REST services. And each service will have its server-side code. And ideally, it will also have its small database on this side as well. So whatever database, whatever the tables are required by the account service, they are stored here. So we have just the tables required for the accounts portion of the application available, just the products related tables stored here and so on. Usually what we do is we create Docker containers. So Docker containers, they allow us to sort of virtualize or isolate sections of our application from other sections. So here we have a container which is hosting just the account service. It contains, let's say if we have a Java-based application, you could have your, let's say, .class files for the service here. Or in case of, let's say, web API, you could have .cs, whatever the compiled files for the .cs files are that we usually use and so on. So these are the services, basically, the code for the service and the database, the tables just for that particular service. So if we just have the accounts tables and so on. So likewise, we have other services, and in the real world, they will all be different Docker container. Will isolate the service from other services and so on. So what's really the benefit of using this approach? The major benefit is, since you're working at a very small level or at a very micro level, so what it means is that you can have multiple teams working on a different service or different subset of the system at the same time. So here we have 1, 2, 3, 4 microservices. So each service could be developed by a different team at the same time. So this is one of the benefits. Another benefit is that you can utilize any technology for developing the service. So for example, this service could be written by using Spring Boot API. This could be written in Node.js. This could be written in ASP.NET Web API, and so on. So they're all interoperable. So even though you're using different technologies, but you can still make all these things work together. So this is another benefit. Otherwise, if you design a monolithic system, usually once you pick the technology, you're stuck to that technology. You cannot change the technology midway through the project, etc., and so on. Whereas here, you can utilize any technology for a small subset of your overall system and so on. And You can utilize any data storage technology. So just like I mentioned previously, you can utilize Oracle, SQL Server, MySQL, or NoSQL sort of databases like MongoDB. So for example, here we could have MongoDB, here we could have CouchDB, here we could have Cosmos DB, etc., and so on. So you can use pretty much any type of data storage technology. So basically, microservices gives you the freedom. Rather than designing everything in a centralized manner, you distribute it. So distributed system can be thought of as microservices concept as well. And another benefit is that you can deploy these services independent of each other. So once you are done with, let's say, one of these services, you can deploy it as long as there are no dependencies on other systems. You can deploy the system that's or subsystem, which is already done. So continuous delivery, CI/CD, which we use in DevOps, can help us a lot when we use this microservices architecture. Otherwise, in a monolithic sort of system, usually we have to do lots and lots of work before we can afford to deploy the system, since we usually focus on the whole system. So that usually takes a long time. Whereas in microservices, since we focus on independent small services, that is why we can afford to deploy a service which is done and so on. So we can have more frequent releases, basically. That's another benefit of microservices. So just like I mentioned previously that we usually get to use agile methodologies, we get to use DevOps, and they all encourage us to have multiple smaller sprints or releases or more frequent releases. So microservices helps us in accomplishing this goal of having more frequent releases, basically. So obviously, there are lots and lots of details involved under the hood, like how do you use Docker? Then there are some more advanced technologies involved as well, like Kubernetes and so on. So these are all covered in a different webinar, which we have delivered in the past. Plus, we also have some courses available on these technologies as well. So for now, we just wanted to cover concepts of what exactly a microservices architecture concept is. So just keep in mind that in microservices architecture, you will have multiple smaller services that are independent and self-contained. Self-contained is another very important aspect of microservices. Each subsystem is a self-contained system. All the databases, all the tables that are required by that particular subsystem, all the services, all the web pages, all the HTML.js files, the REST API services, and so on, all the stuff that's required by that subsystem is contained in an isolated manner, basically. And usually we use a Docker container for this purpose. Okay, so here we have discussed what is microservices architecture. Now, question is, what is Kafka? And how do we utilize Kafka with microservices, since that is the main goal of our this webinar. So here we have discussed we can have multiple smaller systems or subsystems. Now, when we have multiple smaller subsystems, what if they need to communicate with each other? How do you let these subsystems communicate with each other? You can definitely allow these subsystems to communicate with each other directly. So directly would mean whatever port number, IP address you have configured for this particular subsystem or the service, you can expose it to other services, and they can utilize that IP address and the port number to make a direct request to the service. So for example, we have a web browser here. So web browser can say, okay, I need to create a new user account, user registration. Let's say we have that in this account service. So if this end user sends a request to this account service that please register me, then in that case, sure, we are letting the user directly connect to the service. But under the hood, maybe there's a chance that if it's a complex system, it will need to talk to other services. Let me actually give you an example of this one. So say we have order management system, which is a slightly more practical example. And here we want to have order service. So remember, I have order service here as well. So order service at a surface level, it could be a very simple service, but under the hood, there could be lots and lots of details and other microservices required and so on. So if I show you this one again, so order service could require additional services. For example, it might need to call a fraud service to check for fraudulent activities. For example, if some user is trying to send some orders over and over again, you can define some business policies that over a period of 1 hour or so, if you have received maybe 20 requests, then it's a fraudulent activity. Or if the purchase limit has exceeded your threshold value and so on, you can say that it's a fraudulent activity and so on. So order service could call your custom fraud service to detect whether there has been some fraudulent activity or not. Likewise, order service could also make a request to some other service like order details service, which could check for order details. Maybe it might want to check whether whatever order that has been requested by the customer, whether you can fulfill it or not. Maybe you don't have enough stock, or you don't have the product available or something like that and so on. So you can basically call additional services. You can also call, let's say, the email service. So once the order has been received and you have verified that there's no fraud activity or something like that, then in that case, you can notify the end user that, okay, we have received your order, we are working on it and so on. Then once you have verified that you have enough stock available, then you can sort of pass the request and you can say that let's fulfill it. So you can send the request to order shipment service. And then last but not the least, you can also make a request to this invoice service. So you can send an invoice to the end user and so on. So notice that this order service, a simple service which we discussed previously here, is trying to make use of multiple additional services. So in this case, when you have lots and lots of smaller services, then how do you make them communicate with each other? So sure, each service could have its own IP address and it could have its own port number, stuff like that and so on. But if you make a direct request to the service, then there can be two major drawbacks. One drawback would be, what if you have too much load on the system? You're receiving too many requests, then your system might not be able to catch up with all those requests. Maybe some of the requests might start timing out, or the overall performance will slow down a lot. So performance, the load, they can be a major challenge to deal with. Another drawback would be if one of these services is down, if it's not working due to whatever reason, maybe your server like Apache web server, Tomcat, whatever the servers you have used, maybe it has crashed. So in that case, you will not be able to fulfill the request, etc. at all. So what if you don't want to fail the request? What if you want to say, okay, let's wait for the IT department or the sysadmins or whatever team is responsible for fixing the issues and so on, that team should bring the service up and running again. So it should be brought online. And then after that, it should resume, it should work on the request which wasn't fulfilled in the past. It should same spot basically. So we do not want to waste any request at all. We want to fulfill all of them. So basically we want to have sort of a queue basically. So we want to ensure that none of the requests are lost. We want to ensure all the requests are fulfilled. Maybe not in real time because there's too much load on the system, but they should still get fulfilled. Whenever um, the system that's working on the requests, it gets time, it gets the resources, it should work on the requests and fulfill the requests. What I'm trying to get at is when you have too many services and they want to communicate with each other, then making a direct request is not always a feasible option due to these two reasons. You have too much load, or the service is down and you want to wait till the service is brought up and running, and it should resume from from the request which wasn't fulfilled in the past and so on. So this is what we want to achieve. Basically, we want to ensure that we do not bog down the system due to too much load, or we do not start losing the requests. So how do we accomplish that? So that is where Kafka comes into play. Now, before I directly jump, how do we use Kafka with microservices? Let's have a quick overview of Kafka. So Kafka is basically a messaging broker. It's a message broker sort of technology. It's an application-to-application communication mechanism, or service-to-service communication. So when you have lots of services and you want, then you basically utilize this message broker concept, or Kafka, in between, so that you do not lose the requests, etc. at all. And it supports asynchronous operation. So asynchronous means you do not have to wait for the response. So say you send a message to a different service, you do not have to wait for the second service to reply back to you whether you have received it or not. So you want to have some confidence that once a service has sent a request or a message to another service, then you shouldn't be responsible for checking whether it has received the request or not. You should just focus on receiving more requests and just have confidence that, yes, it has been sent to a different service, basically. So we can utilize asynchronous concept when we use this message broker or Kafka. And messages that we send from one service to another, they are essentially the business data. For example, if you have received some order to check whether there has been some fraudulent activity or not, you basically send the order details to this fraud service. It will let you know whether there has been some fraudulent activity or not, and so on. Likewise, other services, they will also receive the messages, and a message is nothing but just the data, basically. And typically, it is in JSON format. When we use this message broker, or we can utilize two different messaging models. We can use point-to-point model, or we can use pub and sub. That's short for publish and subscribe. What's the difference between point-to-point and pub and sub, pub-sub? In case of point-to-point, you will have some publisher or some service which will to another service, not directly, but indirectly via this queue. So in between, you'll have a queue, basically. So message broker allows you to create a queue in between, and this sender service will basically send the message to this queue without caring for the actual receiver. We do not care who's the receiver. We just care for this queue. So think of this queue as maybe if you have used JMS or RabbitMQ or something like that, ActiveMQ. So there are lots of other queuing systems available. Kafka is one of them. Kafka has more stuff as well, which I'll discuss in just a bit. So basically, you send a message to the queue. So that's basically publish. You're publishing a message. And then, or sorry, this is not publishing. We are just sending it right now because it's just a queue. And then on the receiver side, we will have to configure the application or the service in such a way that it continuously monitors this queue. So as soon as a message is received in this queue, the receiver will process it, and so on. So basically, the sender keeps on sending the messages or the requests to the queue, and the receiver will keep on consuming these messages. So here is the point. Only one receiver can receive the exact same message from the queue. Once it has been processed, the message will no longer be available to other services or to other applications, etc. at all. Or you can choose to utilize this pub and sub concept as well. In case of pub and sub, usually we don't call this thing a queue, we call it a topic. So a publisher will send a message to this topic. And then here we can have multiple subscribers. They can subscribe to the exact same topic. And as soon as a publisher to this topic, all will be able to receive a notification and they will receive the exact same message and they can process it. So example of this pub and sub would be this one. So remember I mentioned order service can send a message to the, or it can communicate with this fraud service, order detail service, inventory service, and so on. So here we have this ordered service. It can receive some input or request from some client. We don't care what type of client we are using. It could be a simple web application. It could be application, Android application, Windows application, Linux application. We don't care for it. So this application has sent some requests to this ordered service. And in more advanced cases, all these services, they will be basically part of a Docker container, and we can load balance these services so that only one of these services should receive the request depending on the load on the system and so on. So whichever service it has less load on it, it will receive the request. So regardless which order service has received the request here, it will basically want to send the message to other services like fraud service, inventory service, order detail service, and so on. So, and they should be sent in at exactly the same time. So how do we ensure that multiple services, they receive the message in parallel? We do not want to serialize anything at all. We want to send the requests in parallel, basically. So that's where we get to use Kafka. I'll talk about Kafka in more detail in just a bit. But in short, in between, we will have a topic, which we get to create in Kafka, which is sort of a queue, but it's different than a queue in a sense that a queue, once the message has been consumed, queue, it's no longer available to other services. Whereas in case of topic, once the message has been processed or consumed by the subscriber, or you can the client, then it's still available. Other applications, other services can still choose to use the exact same messages if they want. So it's in our control as developers, how frequently we want to receive the messages, when they should be deleted, etc. and so on. So if you want multiple subscribers to receive the message, same message, then in that case, pub sub is a more popular technique. Like I gave you example, in this case, we can have order service. It can receive the request, and then once the request has been received, let me actually show you that. Here we have, let's say, this order detail topic. So once the request has been received, it will create an entry in a topic. Let's say in this case, we are calling it order created, or you can just call it order received or something like that if you want. So it's a topic. It's a form of a queue, but it's not exactly a queue because you can consume the message multiple times and you can have multiple subscribers and so on. And these services, inventory service, fraud service, order detail service, they have all subscribed to the exact same topic. So as soon as a new message has been received or sent to this particular topic, these services will be able to receive the messages. So here we do have to write the code. The code should be able to receive the notifications whenever the messages are sent to this topic, and then they should be able to receive the messages from this topic as well. We do have to write the code for it, which we discuss in detail in the courses that we have and so on. So basically, we have these services. These are all microservices, and they're all receiving the message from this queue. Now, question is why we are using this topic or queue in between, that's the answer, which I discussed previously as well. We do not want to have direct communication. If order service sends a direct message to this fraud service, and then to orders details service, inventory service, direct communication can slow down the performance a lot. There will be way too much load. And what if one of these services is down? Then in that case, these services will not be able to process that request at all. So in that case, rather than saying, let's get rid of that request altogether and ask the end user to make the request again, why make the end user suffer when we can design the system in such a way that respond to those requests at a later time once the service becomes available. So we basically store the requests. So that's the easiest way to understand this concept. We store the request, and the request will basically contain a message. The details, like what's the product ID, what's the customer ID, what's the date, stuff like that, and so on. So we store the request particular topic, and then other services will subscribe to this topic, and they will receive the requests from the topic either right away, depending on how much load is on that particular service, or in case if the service is down, then whenever the service is brought online in future, then it will be able to connect to the service in future and connect and retrieve the messages that will be processed by the service and so on. So we basically get to store the requests in a queue in this topic basically, and then we get to use this subscriber pub/sub concept basically. So Kafka is exactly this thing. It's a publish subscribe messaging system. You can also choose to use it as a point-to-point system as well, but out of the box, Kafka is a pub/sub system. So multiple subscribers can receive the exact same message, which hasn't already been processed by the service in the past. But you can configure Kafka so that it acts as a point-to-point system, so that once a service processes a request or a message that's in the queue, then it should get purged. It shouldn't be made available to other services, etc. at all. So you can configure it basically. So Kafka is definitely very, very useful when there is too much load on the system, or if you want to ensure that the requests are fulfilled in future, in case if one of the or some of the services they are maybe not working, or they have crashed or something like that, and so on. And in order to use Kafka, we get to use something else as well, which is known as Zookeeper. I'll talk about Zookeeper in just a bit. But in short, it is a distributed coordination system. So I'll talk about it in detail in just a bit. Kafka overall, it's built on top of Java or Scala-based technology. It utilizes JVM basically. It's totally open source. It's very, very fast. It has a very, very high throughput. This is the major benefit of Kafka. So if you want to have confidence that none of them get lost, Kafka is definitely a lifesaver. So basically, once you receive the request, rather than focusing on fulfilling the request right away, store it. Store it in Kafka so that you can have confidence that, okay, it's there now. It's persistent. It will not get lost. And then later on, the services that are supposed to fulfill the request, they will subscribe to that topic, consume the messages, etc., and so on, and fulfill the requests. Kafka, you can utilize it with lots of other technologies as well. For example, you can integrate it with Hadoop if you want to utilize big data capabilities and so on. You can also integrate it with Spark for analytical or data, etc., and so on. So Kafka is definitely a very, very highly flexible system. You can integrate it with lots of other technologies as well. And usually in a microservices architecture-based scenario, your major purpose of using Kafka would be you want to have multiple smaller services, and rather than directly communicating with some service, which can slow down the performance, plus it will become very, very difficult to maintain these direct direct links or direct connections. And in case if the service is down, then it will not get processed. So if you want to have confidence that none of the requests should get lost, Kafka is the best bet, basically. So I'll discuss this overall architecture in more detail in just a bit. So basically, Kafka is highly useful if you want to have a microservices architecture which has very high throughput, where you receive lots and lots of requests pretty much every second and so on. A very common example would be that of Twitter. So Twitter, there are literally millions and millions of received and sent every minute. So Twitter is making use of Kafka as under the hood to ensure that none of the messages get lost. So similarly, Facebook, etc., and so on, where you have way too many messages or way too many requests and so on, that's where it's also useful. And obviously, you can also use it in your other systems, like I mentioned, order management system and so on. It could be customer management sort of a system as well. It could be any type of line of business application as well. So if you have multiple services and they need to communicate with each other, then don't have direct communication between the services. Try to save the messages in this Kafka-based topic, just to have confidence that none of the requests should get lost. So I might sound like a broken record when I keep on saying this thing over and over again, but this is basically the heart and core of Kafka. You do not want to lose any requests whatsoever. You want to save them. You want to persist them. And then later on, whenever the services, they get the time, they get the resources to process the request, they connect to the Kafka topic, they receive the request, process it, fulfill the request, and so on. So high throughput based applications, they can benefit a lot from using Kafka. Plus, you can make your application more scalable. You can add even more services. So right now we have how many services? 1, 2, 3, 4 services. So down the road, you could have even more services. Or actually, even right now, I have email service here. So 1, 2, 3, 4, 5 services. You could have order shipment service as well, which I currently don't have here. You can have invoice service as well. So if you have lots of small services and you want to have communication, then Kafka can let you make your microservices architecture more scalable. So you can keep on adding more services with more confidence that none of the requests will get lost. And Kafka also supports replication concept. What's the meaning of replication? Previously, I mentioned that Kafka gives you the confidence that none of the requests will get lost in case if one of these services is not working. What if the machine where you have hosted Kafka server and you have created the topic where you're storing the messages, what if that machine crashes? So now we are saying that the Kafka server has crashed. So how do we prevent the system, or how do we ensure that the system should continue to work? So in that case, we basically get to use replication concept in Kafka. So Kafka can be hosted on multiple machines, and they can all be replicated. They will all have the exact same topics. So usually you have sort of a master, or it's also officially known as the leader. So you have a leader node in the Kafka cluster where you have a bunch of topics. Each topic will have a bunch of messages. So if the leader has crashed, then one of the alternate replicas will take over. It will become the leader. And Kafka server automatically ensures that if the leader has crashed, then some other Kafka node should take over. It should become the leader and so on. And it replicates the data. So you can have multiple replicas basically. So if you have multiple physical machines, each machine can host a separate Kafka server, and they can all be replicated. So this way, if one goes down, then the other one will still be available. And this way, all the services, they will continue to work. So basically, we want to ensure that in a microservices architecture-based system, not just the services are load balanced and replicated, but the Kafka, the queuing system, or the message broker system, that is also replicated as well. So that if this message broker system has crashed, then it should still continue to work, or should still continue to work. And stream processing is another benefit. So like I mentioned that in Kafka, you can basically utilize the pub/sub concept. Publisher can send requests to the topic, and subscribers, they can subscribe and consume the requests. So you can process things in almost real-time manner. So you keep on sending the messages. They will get stored in the destination side, the receiver side. We will have the application which will connect to the topic, keep on processing the requests, and so on. Another example of this streaming processing concept would be that of IoTs. Not everyone uses this concept, but slowly and gradually it is becoming very popular. So Internet of Things, IoT, so they are basically sort of devices with sensors. They can receive the data. Like you can have the thermometer, you could have pressure, you could have weather information sort of data, you could have other sort of sensors. You can even have mobile devices acting as sensors. They can receive the data, and you can store them in a Kafka topic. And then later on, services can take all the time in the world. They can connect to this topic, process the requests one at a time, and so on. Otherwise, IoT devices can bombard the system with way too many requests, and that can bog down the performance. It can slow down the performance a lot, or it can almost crash the system as well, depending on the load and so on. So to ensure that we don't have any system failures, we store the data in a Kafka topic, basically, which is a very, very fast mechanism for storing the messages, the requests, and then later on the services can receive the data from the topic, process it, and fulfill the request and so on. So you can basically utilize the streaming concept as well, where you almost receive the data in real-time manner, and you do not want to lose anything at all, and so on. So data loss is not bearable. We do not want to lose any data whatsoever. In Kafka, we get to use some important concepts. Like I've mentioned, topic already. So topic is basically sort of a queue. It's not exactly a queue, but it's a form of queue. In a topic, we get to store messages. Publishers, they are essentially the services. They send the messages to the topic, and subscribers, they connect to the topic, process the request, and so on. The publisher is also officially known as a producer. So producer is basically nothing but just a service, and you're assigning it a role. You're saying that it's a producer. It will create messages. It will send the messages to the topic. And consumer is basically sort of the client. It's the subscriber. It connects to the topic, receives the requests or the messages, processes it, and so on. And another very important concept which we get to use in Kafka is that of broker. So broker is sort of a server, basically. So Kafka is composed of at least one server, which is actually also known as a broker. So broker is sort of a Kafka service. This is what that makes things happen. It ensures that we are able to receive the we are able to send the requests, receive the requests, and so on. So publishers, subscriber, etc., they work because of this broker. And broker will basically be an instance of Kafka, and you can have multiple brokers Ideally, in the real world, you'll want to have each broker running on a separate machine so that if one broker crashes, then the other broker should take over and so on. And each broker will basically have a replicated copy of the topic or topics, depending on how many topics you have. And overall, this entire thing is also known as a Kafka cluster. So Kafka cluster is composed of at least one broker. So basically, our goal is to ensure we do not lose any request, any message whatsoever. We want to fulfill all of them. Then let me talk about a Zookeeper a little bit. Zookeeper is another open source project. It's basically called Apache Zookeeper, and it's a prerequisite for using Kafka. You cannot use Kafka without this Apache Zookeeper. What is Zookeeper? Zookeeper is what that makes the replication possible. So if you have machine number 1, you have a broker here with a bunch of topics here, and you have a machine number 2, and you want to ensure that it has the identical, it's the exact replica of the first one. So you want to have a replicated copy of the broker basically. And right now we have just 2. You can have as many as you want. So how do you ensure that they are all replicated? So that is basically the responsibility of Zookeeper. So Zookeeper ensures that all these nodes, they are replicated. All these brokers are replicated. All the topics are replicated and so on. So it basically gels this Kafka system together and so on. Without Zookeeper, we cannot utilize Kafka. Then let me show you a brief demo of Kafka here. It's a very straightforward demo, actually. There isn't anything fancy here, but it will let us, or it will help us in understanding, okay, we need that many number of components in Kafka and so on. So here, in this terminal number 1, I'm going to start my Zookeeper. Zookeeper is up and running. In the second terminal, I'm going to start my Kafka server. Right now, I have a single broker. I do not have replicated or replication in place right now, since I have just a single physical machine or a single virtual machine for this particular scenario. And then here, I'm going to start a consumer just so that we can see what messages we have received and so on. In the real world, some service, like you could have the order shipment service, you could have invoice service or something like that and so on. For now, I'm just going to utilize a simple console-based application, which will let us receive the messages. In the past, I've already sent quite a few messages to my Kafka topic. And then last but not the least, I have a simple Spring Boot application here, which is going to act as a publisher. It will publish a message to the Kafka topic, and this consumer will let us see what messages are there in that Kafka topic. Right now, it is telling us that we already have quite a few messages from the past. So here I'm going to send just a simple message here. Let's say we have a simple sales order 1 message right now, but in the real world, you'll want to send JSON sort of data. So if you have a purchase order request, you'll want to send the purchase order request in a form of a JSON object to the Kafka topic. So right now I've sent it, and it will get sent to the topic, and this consumer, it has subscribed to the Kafka topic, and it's letting us know that we have received this topic. So basically, publisher and consumer, pub sub concept is getting utilized, and in between we have Kafka. So you have sort of 2 services, any 2 services. So for example, like I mentioned previously, we can have the order service. This is, let's say, the publisher, and then we have the fraud service. Actually, I have fraud service, order detail service, inventory service. They're all the subscribers. They're all subscribing to the same Kafka topic, which I have here. Let me undo this stuff here so I can explain it again. Okay, so basically we will have, so some end user level application or a web browser here. Web browser will be used for sending the requests to the server. On the server side, we will have order service. It will receive the request, and rather than sending the request directly to some other service, for the sake of validation, etc., and so on, it will basically send it to this Kafka topic, just so that it can have confidence that nothing will get lost. And then here we have three microservices: fraud service, inventory service, order detail service. They have all subscribed to the same. They will receive the request, they will process it, and then once they are done, they will use another topic to write another message to this Kafka topic that yes, we have processed it, we have validated the request, and whether it has passed or it has failed. So fraud service, order detail service, inventory service, they will write the status of the validation check to this Kafka topic. It's a different Kafka topic. And then on this side, this order detail service has also subscribed to this Kafka topic. So once it has received the validation status of the request, after that, we can have the order shipment service. It can subscribe to this order validation topic, and it can fulfill the request. It can ship the order to the customer. And then we can also have invoice service as well. It can also subscribe to the same Kafka topic. It can also fulfill the request and send the invoice to the end user and so on. So basically, the role of Kafka in a microservices architecture is to ensure we have communication taking place between these services. And although you can choose to have direct communication, or you can also choose to write some data to a database, like it could be Oracle database, MySQL database, SQL Server, but they will be very, very slow. We don't want slow. We want to have confidence that none of the requests get lost. And we should be able to handle the load on the system. We should be able to make the system more scalable. So that is the reason why we are not choosing to use databases in between. We are choosing to use these Kafka topics or the message brokers. And definitely, if you have database requirement, go ahead. You can still choose to have a service here which can subscribe to the topic, and it can receive the data from the topic, and it can write the data to the database as well. So you can still databases as well, but don't write it directly to the database. It will be very, very slow. Write it to a Kafka topic. It will be very, very fast. Then you can take all the time in the world and write it to the slower components like databases, etc., and so on. Basically, Kafka with microservices in a nutshell. So definitely, there are lots of details involved, like you can also utilize the ELK stack, like Elasticsearch, Logstash, Kibana stack with Kafka. And lots of major companies, they are using Kafka these days. And definitely there are lots. We have a couple of courses on Kafka. We have Kafka for application modernization and developing microservices courses here as well, in case if you want to see how to develop microservices. Whereas if you just want to focus on Kafka, we have this particular course. Okay, so any question regarding Kafka with microservices concept? Question, does the web browser interact directly with the Kafka, or a browser calls a service? Good question, actually. So it depends. You can definitely have a web browser or application running in the web browser. Like you could have JavaScript, etc., and so on, or jQuery, etc., and so on. It can send a request to the server side and write the message to the Kafka topic directly. You can definitely have that. But if you load balance your service, this, let's say, order service here, as long as this order service is not available, notice that it's not doing any heavy work here at all. It is relying on other services. Fraud service, order detail service, they all will eventually connect to the databases to verify that whether we have enough stock in the inventory or not, whether there's a fraudulent activity or not, and slower components or the slow processing is being performed by other services, not by this main service. So your direct point of contact of the web browser is just this service. So as long as it's a very lightweight service and you have load balanced it, then it's okay to send the request directly to this service. And then this service should only be responsible for sending the request directly to the Kafka topic. And then these slower services, they will want to connect to the Kafka topic and process the requests. So basically, the key thing is how heavyweight your service is. So if it's a very lightweight service and it's load balanced as well, it's okay to send the request directly from the web browser to the service, as long as it's writing the message to the Kafka topic as well. There's another question: can Kafka aggregate data from different services? So definitely, yes, Kafka can also be used for aggregating data as well. In most cases, you will end up writing your own custom code for aggregation and so on. So for example, remember I mentioned fraud service, inventory service, or a detail service. So they will all receive the request or the message from the same Kafka. They will run in parallel. They're all running in parallel. And they will write the validation status to another Kafka topic. We will end up having 3 separate messages in this validation Kafka topic for these 3. And then this order service will want to aggregate these 3 messages. So this order service needs to know whether this status is valid, this status is valid, this status is valid or not. So it will want to aggregate the statuses basically. So here when we receive the separate topics, we can aggregate these statuses, messages basically. So that is custom logic in this order service will be responsible for aggregating. We also get to use something in Kafka topic, which is known as a keyed message, which helps us in aggregation or in verification of the messages and so on. Okay, any further questions? So the slides will be hosted along with the recorded session as well. So thank you very much, guys. It was a pleasure to be here with you for this webinar.